Welcome to today's Explainer. We're diving straight into how scientists actually track and, more importantly, predict massive environmental changes in some of the most rugged terrain on Earth. We'll be looking at their core objectives, breaking down their AI-driven spatial regression methods, and examining their pretty alarming results, which point to a huge future loss of dense forests. Let's get right into it. So, our focus today is this really compelling study recently published in the journal Environmental Challenges. The authors here had a massive three-part objective. First, map out the historical vegetation dynamics. Second, pinpoint the exact environmental and human drivers forcing these changes. And third, this is the really cool part, use artificial intelligence and geospatial math to predict exactly what this landscape is going to look like by the year 2030. Okay, let's dive into this. The Chittagong Hill Tracts, or CHT for short, down in southeastern Bangladesh, is this incredibly vital, ecologically rich region. We're talking dense tropical forests, deep valleys, and really steep hills. Now, because it's so rugged and remote, doing traditional ground surveys, it's basically impossible. And that makes satellite remote sensing absolutely essential for tracking what's actually happening to the forests out there. Here's our roadmap for the explainer. 1. Collecting the data. 2. Classifying the landscape. 3. Neural network predictions. 4. Spatial regression drivers. And finally, 5. The shrinking green. Section 1. Collecting the data. Tools of the trade. To get started, the researchers had to choose their satellite. They deliberately went with Landsat 4.5 images for the years 1989 and 1998, and Landsat 8 OLI for 2018 and 2024. Now, you might be wondering, why not use MODIS or Sentinel? Well, MODIS is just way too coarse for detailed vegetation mapping in such a complex, heterogeneous landscape like the CHT. And Sentinel-2, it's great, but it lacks the full temporal coverage they needed going all the way back to 1989. Landsat was basically the perfect time machine for this job. But it's not just about taking pictures from space. They had to figure out why the vegetation was changing. To do this, the researchers basically acted like spatial detectives. They pulled elevation data and calculated the slope of the hills using the SRTM digital elevation model. Then, to measure the human impact, they grabbed population and settlement grid data from the global human settlement layer. And for moisture, they actually extracted that directly from the Landsat images themselves. Which brings us to the core math of the study. How do you actually measure greenness from space? You use NDVI, the Normalized Difference Vegetation Index. Look at this equation. It's simply a mathematical ratio of near-infrared and red light. Since healthy plants strongly reflect near-infrared light, this math is perfect for mapping plant density. They also used NDMI, which swaps out the red band for shortwave infrared. Why? Because NDMI measures the actual water content and moisture stress inside the vegetation. Section 2. Classifying the landscape, making sense of pixels. Of course, before you analyze anything, you've got to clean the raw data. Think of this pre-processing kind of like tuning an instrument before a big concert. The researchers ran geometric and radiometric corrections so that every single image from 1989 to 2024 perfectly aligned on the Earth's surface, using the UTM Zone 46 coordinate system. Then they resampled everything to a uniform 30-meter pixel size to make sure it was an apples-to-apples comparison. Now, what's really interesting about this slide is how that NDVI math becomes reality. Those NDVI values, which range from -1 to +1, are sliced into 4 distinct physical classifications. Anything under 0.18, that's your bare soil, water, or built-up areas. Between 0.18 and 0.35, you've got sparse vegetation, like low shrubs. Moving up to 0.35 to 0.5 gives us moderate vegetation, like crops or fragmented forests. And anything above 0.5, that's your dense, high-density jungle. But hold on, how do we actually know these automated classifications are right? Well, you have to run an accuracy assessment. They use the kappa coefficient, which is equation 7 here. This is crucial because it proves the model's accuracy isn't just a lucky guess. The researchers generated 1,000 random points across the map, checked their automated map against real-world reference data, and hit an impressive overall accuracy of over 90%. So yeah, the math definitely works. Section 3. Neural network predictions. Seeing the future. To start peering into the future, the authors first created a transitional matrix using equation 8. You can kind of think of this as a mathematical time-lapse. It quantifies exactly how much area shifted from one specific vegetation class to another between the decades. By dividing the area of a changed class by the total area and multiplying by 100, they could clearly see the flow, like exactly how much moderate forest degraded into sparse shrubs over a 10-year period. Next, to actually predict the year 2030, they set up an artificial neural network, or ANN. Here's how they did it. Step 1, generating training data. They fed over 5,000 random points from their 2018 and 2024 maps into the model so it could learn. Step 2, feature selection. They handed the AI spatial variables, things like elevation and past land cover. And finally, step 3, model training. This is where the AI chews on all that data to learn the complex, hidden rules of exactly how and why the force changes over time. Let's demystify the intense math behind that ANN. Equation 9 is cross-entropy loss. In plain English, this just measures the mistakes the model makes during its training phase. Equation 10 is the atom update. This is a really clever mathematical tweak that basically rewires the network's brain to fix those mistakes and get smarter. And then equation 11 is the prediction. Once the AI is fully trained, this equation spits out the final predicted vegetation class for the future Mac. Section 4, Spatial Regression Drivers, Finding the Root Causes. Now we need to know why this is happening. They started with ordinary least squares regression, or OLS, which you see here as equation 12. Think of OLS as a global baseline. See how it takes our greenness metric, NDVI, and tests how it's impacted by all our variables: slope, elevation, moisture, population, and settlements. It's trying to find one overarching rule, like does human settlement generally have a positive or negative impact on greenness across the entire map? But there is a major catch. Why did they need to calculate the global Moran's eye, which is equation 13? Well, the researchers used this to test if the errors from that global OLS model were spatially clustered together, and guess what? They were. This proves that a one-size-fits-all global equation completely fails here. A hill in the north doesn't lose its trees for the exact same reasons as a valley in the south. The landscape is just too incredibly complex for one simple rule. Because the landscape is so varied, they had to upgrade to geographically weighted regression, or GWR, which is equation 14. We use GWR because it specifically allows for local spatial variation in the relationship between NDVI and its drivers. Instead of one global rule, it calculates unique, localized relationships for every single grid cell on the map. It scientifically proves that human and environmental impacts literally change depending on exactly where you are standing in the Chittagong Hill Tracts. Section 5. The Shrinking Green. Results and Discussion. All right, let's leave the equations behind for a second and look at the reality on the ground. Tracing these maps from 1989 to 2024 reveals a really stark visual story. Look at the light green, which represents our moderate vegetation. It is steadily shrinking. Meanwhile, that lime green color, the sparse, shrubby vegetation, is clearly expanding like wildfire. All that math we just talked about, it's manifesting as a slow, steady loss of healthy forest over 35 years. When we put the spatial transition maps side by side with the complex flow diagram generated by the transitional matrix, the alarm bells really start ringing. Just trace those thick bands in the diagram. You can see ecologically rich, moderate vegetation degrading and flowing directly into the vulnerable sparse vegetation category decade after decade. It is a stunning quantitative visualization of an ecosystem under severe human pressure. And finally, we arrive at the culmination of the artificial neural network's work, the 2030 prediction map. By feeding all those historical trends into the AI, the model predicts continued, severe strain on the ecosystem. By 2030, it expects sparse vegetation to rise to nearly 30% of the entire region. Meanwhile, those dense, mature jungles, they will be clinging to a mere 1% of the land. 1%. Which leaves us with this absolutely crucial question. Can spatially informed strategies reverse this 2030 prediction? What we've learned today isn't just an academic exercise in tracking a shrinking green landscape. This methodology provides the exact, localized data needed to spark urgent, climate-adaptive conservation before time runs out. The AI has shown us a really grim future. Now it's up to us to change it. Thanks so much for joining me on this explainer, and I really hope this deep dive sparked your curiosity to learn even more.